event-related potential.
Thank you.
Yes. The phenomenon you're talking about with your studies, is that why, like, if you pull an all-nighter for an exam, you get to the test, you kind of, like, it takes you so much longer to, like, put material together? Is it just because your brain's, like, exhausted?
Well, it is because your brain's exhausted, and part of it has to do with the encroachment of sleep, and part of it has to do with while you're asleep, the glial cells in your brain are working overtime to recharge your brain, to give you back the neurotransmitters that you lost, and also to organize that information. And so if you let it go too long, you're actually losing the resources you need to think.
Okay.
And so amplitude and deflection, EEG, the size of a waveform, and then morphology, the shape of a waveform. People don't use that in experimental psychology much, but we use it in clinical psychology a lot. It is very heavily used because there are certain shapes you should not see in the human EEG no matter what. Period. You should never see them. And there's hundreds of them that you just never should see. And you kind of have to memorize them because they're pretty unique. Yes?
Are these shapes are considered frequently associated?
Well, a lot of them are associated like with epilepsy, having had a stroke, things along that line.
What about like brain tumors?
Yes. Most of delta is associated with brain tumors. A brain tumor, and it depends on whether it's encapsulated or not, but it is a waveform. Cortex, not only, the thalamus regulates, reticular nucleus regulates your thalamus, regulates your cortex. But the cortex itself oscillates at its own frequencies. A tumor doesn't have that roadmap, and so it won't oscillate along with the cortex in a similar pattern. And typically it's like a delta, it's all doing its own thing.
Is it creating delta because it's putting pressure on the brain?
No idea, because it's based on what kind of tumor and what's happening. All right. We talked about the general definitions of these terms. Let's get into the actual quantification of these terms. I know this is not the most rockin' thing, but there's only 10 more minutes, which means you can do a lot of alpha. So, peak-to-peak frequency count from 1 to 1 is considered a cycle. If you're thinking about it as a sinusoidal waveform, one whole circle, 360 degrees, that's a cycle. I always think of bikes. I think cycle, and I go from the top around to the top again. That's a cycle. And so the frequency count is, hey, 1, 2, 3, 4. I say that, and then when I get on a real EEG, I go, now wait, is it 1, 2, 3, 4, or is it 1, 2, 3, 4 every time? Frequency is the number per unit of time. It really doesn't matter what you measure them in. We measure them in hertz because we measure everything in hertz with waveforms. Hertz is just the number of times that something happens per second. And our beta, our thinking, waveform is beta, happens at 20 hertz, which is also the lowest sound we can hear. It's just a little below our threshold for hearing. So it happens below what we could hear. And they run from 0.5 hertz all the way up into the hundreds. We really can't measure above the hundreds on the surface of the scalp. It just doesn't get through the skull. It's just not going to happen. So when we measure time, here's the big deal. Because I'm going to slip and I'm going to do this all the time. I'm going to go 1 second, 1,000 milliseconds. Because it's just the way I think. 1,000 milliseconds are in a second. Everything in the EEG is measured in milliseconds. And there's 1,000 of them in a second. Here are what they look like. So, here we have delta at 2 to 4 hertz. Notice that it's very big and very slow. Here we have alpha at 10 hertz, and so it's shorter, but it also can be quite large. Here we have theta, and it's a little faster. And then notice that the beta at 13 to 30 is pretty small. And so each of these is depicted across 1 second of time. And so just in general, that's what they look like in relation to one another. Yes?
Why the space? Why 4 to 8 hertz? Why not just 8 hertz? And why just 2 to 4 hertz? Why not 4 hertz? Is a hertz per cycle?
Yeah.
It's like that.
It's yeah. And the reason why it's 2 to 4 hertz is because they all fall in the range. Remember, you're a human brain. You are not a computer.
Oh.
We have a range of what we consider delta and a range of what we consider alpha. And so it's not perfect. Yes? No?
No, I was counting, sorry.
And so, and this is, all right, the next slide is gonna hurt.
Could you hold this one?
Yeah. So this one is associated with relaxed attention, and I said this is 8 to 12 hertz. This is at about 10 hertz. At 8 to 10 hertz, it's low alpha. It's associated with falling asleep. High alpha is actually associated with attention. And so there's a variety of waveforms that are under here. Depends on where they are and what the context is, which we're going to talk about. I'll break it down. Amplitude. This is the magnitude. And I talked about morphology and got real super lazy here and decided not to type it. But here, we're looking at especially shape, like if it's spiky or it's sharp or it has a complex. A sleep spindle starts and it rings, it goes, and so it starts really heavy and then it just cycles and then it disappears. And so it's all one waveform, but it's a complex. And so we can measure the amplitude from the baseline, which by the way, we don't know. You noticed earlier on this graph, I said, how do we measure the baseline? Mm-hmm. We don't really know what the baseline is, but we're gonna take a guess. And, or you can measure it from peak to trough. We know what both of those are, but it only works if you have both peak and trough. We're gonna look at new waveforms that only have peaks. Stupid things. All right. Here's the freaky thing. Waveforms, once they combine together, you stick some alpha and some beta. This is alpha and beta stuck together, just from the preceding graphs. Nothing more complicated than that. And this is what happens. Thank you. They can be combined in any way. And so, here this is alpha and beta, and I believe what we're looking at here is I set the beta off phase to the alpha, and so it was just off phase a little bit, so that its peak and the alpha peak did not match at any point in time. And then you get this type of waveform. It is exactly the same phenomenon on the top and the bottom. Exactly the same. They're just an incidence of when they occurred. Yes?
Are those troughs negative?
Yes. And so, if we were to do a Fourier analysis and break these apart, we'd have the same alpha and the same beta.
Are they, what is the unit we're using to measure them? Microvolts?
Yes.
Is it?
And so, the long story short is, there ain't nothing that you can really resolve by just looking at raw EEG until you pull it apart. There are a few things, if you know enough about the human brain, but it's